In science, we often pursue the known unknown. It is the gateway to the unknown that we wish to stumble upon and to access.
This is the Discovery Files podcast from the U.S. National Science Foundation. I'm Nate Potker. Concrete is all around us. It's in the buildings we live in, the sidewalks we travel on, and the infrastructure that allows us to have fresh water. Concrete is a tough material, but over time and given the right conditions, it can crack and crumble and fail. Advances in material science and processing can enhance concrete's resilience, recyclability, and long-term durability, enabling significant economic and societal benefits. We're joined by Reza Moini, assistant professor in the Department of Civil and Environmental Engineering and an affiliated faculty at the Andlinger Center for Energy and the Environment at Princeton University, where his lab is developing resilient materials and structures with bio-inspired designs for architected civil engineering projects enabled by automated manufacturing robotic systems. Professor Moini, thank you for joining me today.
Thank you for having me.
I'd like to start with just a bit of your history. How did you become interested in concrete?
Right, so my interest in concrete started from my undergraduate studies. When I first took the course that was actually required in the curriculum, Concrete Material Science and Technology, it really fascinated me how complex the organic chemistry of the most commonly human-made material was, and how the chemistry controlled the material microstructure, or essentially the fabric of the material, if you wish. That then governed in courses that I later learned the constitutive mechanical properties and the resulting performance of these materials.
For the next few questions, I want to ask you about a few concepts that are at play in your work. Strength and toughness. What are strength and toughness in concrete?
Strength and toughness are two fundamental properties that play a significant role in the design and the longevity of materials, in this case of concrete, that is used in urban and infrastructure sector. In that context, the strength is often one of the key mechanical properties that we need to design roads and structures, for example, for certain load-bearing capacities. Fracture toughness, on the other hand, is the energy required to propagate an existing crack. In other words, fracture toughness is the critical resistance above which the material will fracture, or if there is a crack, it will continue to extend. This property is relevant to civil infrastructure design, given that the degradation and the progressive damage due to the mechanical and environmental loading conditions in various parts of the country and various parts of the world.
And we're talking about traffic and cars and weather impacting materials here.
Absolutely.
Okay. For the next concept, I want to ask you about rheology. How does rheology impact concretes?
Right. So rheology essentially is a field between solid mechanics and fluid mechanics, in which people study solids and liquids. In rheology, people study deformable materials such as gels and suspensions and colloidal systems across various length scales and time scales. There are materials that are neither perfect solids or ideal liquids, and have some properties of both. The question people often ask in the field of rheology consists of applying stress and measuring strain, or vice versa, and asking what does the material constitutive relationships, constitutive properties are, and how do we understand them. When it comes to cement and concrete, cement is a hydraulic powder, meaning that it gains strength over time by reacting with water, by chemically reacting with water that is mixed in the process of concrete production. Concrete then becomes a deformable material when it is in its fresh state. During the production, it needs to be fresh so it can be transported, it can be poured. And after a few hours, concrete solidifies and gains the strength due to this hydraulic reaction. So in studying the rheology of concrete, people study the deformation of concrete by trying to quantify, for example, its viscosity, how it begins to flow, how it ceases to flow throughout the hydration over time.
Okay, the last concept I wanted to ask you about. What is additive manufacturing in the world of concretes?
Of course. So additive manufacturing, or colloquially as people may understand it as 3D printing, is a layer by layer and lamella by lamella process to fabricate materials and structures. Depending on the processing techniques and material, It involves flow, it involves extrusion, it involves deposition and solidification. Therefore, it lends itself as an interesting subject for rheological studies. Additive manufacturing also in some ways is a slightly more advanced fabrication tool than conventional processing ones, in that it enables engineers and researchers to somehow control the types of properties of the materials and the interfaces locally, thereby controlling the bulk properties and performance of the material.
You mentioned 3D printing concretes. Does working in that form require special treatment or special additives in the cement mixture, in what becomes the concrete?
That's a great question. To answer that, I need to contextualize things a little more. I think for most of the modern era, the construction techniques that we've been using have remained limited, mostly due to the constraints in the material properties itself. The lack of progress, I should add, that in developing more advanced tools and techniques has demoted inventing new arrangements of materials and structures. We are at a time in material science and construction technology that the advent of new techniques can be utilized to develop new types of concrete, for example, through additive manufacturing. These abilities to extend and customize the additive manufacturing process allows us to go beyond what currently is even possible through additive manufacturing. And so there would be special aids, if you wish, right, in how we formulate the material, in how we design the fabrication methods and the tools that would then synergistically contribute to the rethinking of the material itself. Because the process needs to be developed from scratch, it allows the special considerations of materials limitations and design in synergistic ways that we couldn't couple before. This leads to the ability to reimagine concrete from a materials, from a mechanics, and from a structures standpoint.
So my wife worked in real estate for a number of years, and I'm sort of familiar with 3D printing concrete homes where they're kind of following along the wall. When you're working with that extrusion method, does the concrete need traditional reinforcements like rebar?
Right. So this has been a common question about whether we should use additive manufacturing to reimagine what concrete is as a composite material, as a material that has different constituents, or we should adapt it to what we currently consider what concrete is, or what reinforced concrete is, which is a composite of concrete and steel rebars. My take on this is that we have the opportunity to reimagine concrete as a new types of composite. The ability to design materials arrangement lends itself to multimateriality and rethink what composite is. Reinforced concrete was only one type of composite that we came up with that we could envision to, for example, make high-rise buildings, right? We can now engineer specific types of properties using the specific arrangements of a single material or multiple materials, and what we refer to as, in my lab, as materials architecture. These are materials with purposeful arrangements that have properties better than their constituents, thereby are materials that can be exploited to rethink their constitutive properties.
That leads well into asking you about architected techniques in design. What are some of the ways you're approaching reimagining how you're using concretes? So
in our work, we often look into biological materials with distinct design motifs that elicit unique one or more mechanical properties, or otherwise mutually exclusive combinations of material properties, for example, strength and toughness. Nature is a great starting point to look for underlying mechanisms around which relevant hypotheses for engineering counterparts can be postulated and probed through experiments, through computation. But we still need ability to fabricate these materials. So we advance our fabrication methods through using additive manufacturing techniques, through advancing robotic manufacturing processes that enable these designs. so that we can formalize and extend questions around how does design controls the properties, how can we learn from clever and purposeful internal arrangements of materials, spatial arrangements of materials in space, in natural systems, and address some of the drawbacks in engineered materials. For example, some of the drawbacks in mechanical properties of concrete, or its lack of resistance to fracture.
How is the Moini lab taking inspiration from these natural forms?
There are several architected designs of inner arrangements of materials that we explore in our lab, some of which are inspired by the studies of biological materials that has been carried out by our colleagues. I can give you one or two examples here to our audience. One is a nacre-like concrete that was inspired by the inner arrangements of shells. It consists of, the shell consists of a brick and mortar type of architecture for the sake of visualization, where the brick is a brittle material, brittle natural material, making up 95% of the structure, and the mortar is a biopolymer making up the remaining 5%. The toughness of this natural biological material, the shell, the mother of pearl, is several orders of magnitude larger than its brittle aragonite constituent. And one of the key mechanisms that induces toughening is sliding of the bricks over one another in the process of damage and fracture. What we did was engineering tough nacre-like tabulated cementitious polymeric composites inspired by the brick and mortar arrangement of mollusk shell. We discovered that we can use laser processing to engrave and build intentional defects as a way to make the material stronger, or to entirely separate the sheets of cement paste into discrete hexagonal tablets. You could use this process to create essentially those bricks in a relatively fast rate. We then used a lamination process to layer by layer form the composite. One can envision an automated or additive process to do so. We also had to find the appropriate elastomeric material that has the right constitutive properties and satisfies the necessary mechanical properties to elicit the underlying toughening mechanisms. The goal here was to develop not just the bio-inspired geometry, which sometimes is practiced, but to engineer the underlying tablet sliding mechanism that we have learned from nature and extending it to concrete materials. We found that we can generate interlayer deformation, tortuous crack propagation, guided by the tabulated design, by the hexagonal design of the architecture of the brittle material, and crack bridging, where the soft material bridges behind the crack as the crack propagates into the brittle interfaces between the tablets, but not inside the tablets. These are the three main toughening mechanisms that then led to an increase in fracture toughness, or the resistance to fracture, in the bulk composite cementitious material, mostly made of the cementitious material. And then this sliding prevents, again, tablets from fracture and failure, we found, which then led to enhancement of the fracture toughness and ductility by 17 and 19 fold, respectively, compared to monolithic cast materials.
That seems to be a pretty good return on investment there with that statistic.
I believe so.
So kind of thinking about next steps and bringing these technologies and techniques into the public sector, what are the challenges scaling these things into buildings and roads?
So there are many companies and corporations that are already working on scaling up these additive technologies from laboratory small scale to benchtop to larger and larger scales. At the same time, discoveries are being made through the great work of our colleagues in many academic institutions around the world and the United States in the lab in these areas. This has created really an accelerated surge of discoveries and rapid developments in the area of sort of concrete and additive manufacturing and design that to me is somewhat unprecedented. Not always the discoveries in the lab may translate to the field, or the practitioners or the market may not necessarily pick up on every discovery that is made around the world. the market decides that. This is not the case here when it comes to design and fabrication of new materials, more mechanically resilient materials, more functionally efficient materials and structures. To give you more context, since 2010, the advancements have continued both on the fundamental aspects and in the field by scaling up the additive manufacturing techniques, from materials to components, and from components to building envelope, and even more recently to even marine structures at tens of meters in scale. However, all that said, scaling up is not necessarily the bottleneck, in my opinion. In many cases, there are several technical challenges that has to be addressed and has to be invested, and research grants and proposals have to be made. Many resources and efforts and time has to be spent on addressing that. But from a technology utility perspective, from a more abstract perspective, I think we have the opportunity, if not the obligation, to reinvent and redefine what materials and structures mean to us and what are they going to look like in the next decades. Something we often underestimate is that, I think as a community, is that the role of scientific discovery, whether it is through formal or exploratory approaches, we may not need to build in the same way we build today in the next few decades. And in order to sort of grapple with that concept, or if we grapple with that concept long enough, I think we realize that technology has a lot more to offer that allows us to reinvent and re-envision the material as we scale up the technologies. And this is something that it's often, I think, talked about in developing the technology, not for today, but for a sustained period of time.
So thinking about some of those fundamental advancements that you've made, I want to ask you about your career award. How has NSF support impacted your career to date?
I think NSF has a very crucial role for academic institutions and for discovery. But I wanted to talk also a little bit about the other types of roles that NSF has. I think demystifying what science is and what it is not, in an era when we witness such a rapid growth of new technologies, I think it provides a baseline for the society to adapt to the evolution of everyday tools and techniques that comes our way in public way of processing information, and processing how to even change our day-to-day human life. So it is even goes further beyond what science is and what is its impact on engineering and on the society. It goes into really what how does it affect our thinking of our perception of the outside world. And I think, going back to NSF, I think the National Science Foundation of the United States plays a crucial role in promoting science and scientific discovery by supporting researchers and engineers being able to pursue their questions, propose their question, and pursue answers towards them, which in many cases leads to giant leaps in our understanding of the physical world and inventions that benefit the society. This process allows for the training of the next generation of young thinkers that work on specific problems and programs supported by the foundation. We cannot answer the fundamental questions we postulate every day without the support of entities such as National Science Foundation that support research grants, that allows for such type of training and mentorship for the young minds to take place that would then carry the torch forward. I specifically, for our lab, myself, I think specifically would like to use this opportunity to thank the Engineering Civil Infrastructure Program, which has always been supportive in proposing new concepts and ideas surrounding civil infrastructure materials and structures, advanced manufacturing program that has really stepped in to allow for transformations in the manufacturing domain to translate into the infrastructure domain. And specifically the Young Career Award, Young Investigator Career Award program that I've received and has supported me and the research of me and my group in the past 3 years. It goes without saying that these efforts have had not only an impact on my career, but I hope that has had impact on the scientific community and making very small step discoveries, but more importantly, on the people, on the students and the postdocs who work on these types of projects that can foster their creativity and sense of adventure.
So the last thing I wanted to ask you about today is thinking about the future of your research and really the future of concretes in general. Where do you see these things going over the next few years?
Thank you for asking that question. I think materials and structures that we will design in the next 10, 20, 30 years won't be the same as the ones we design today. I think I alluded to that earlier. And so the meaning of concrete, the meaning of materials in general may change in almost every aspect we know today. Whether you think of it as a material, whether you think of its mechanics and fundamental aspects, or you think of it as a structure, given the advanced manufacturing techniques, but also the advanced computational design capabilities that are only going to grow. All right. So I think we're only scratching the surface also with not just manufacturing and design and computation, but also with robotics in the world of concrete or construction materials, or more broadly speaking, in the world of engineering. We may very well be at the cusp of a paradigm shift, in my opinion, in the next several years, due to the growth and the ability to move from automation to autonomy in robotics, in construction. Many efforts have already been kicked off, and so I think this is just the beginning of some new times in the field. As our tools of design, computation, and autonomous robotic fabrication advances, I think we might be able to redefine these materials and be able to engineer and infuse and embed specific properties or properties that were difficult to achieve before into the materials of the future. The properties that might be strange today or to think of, but I think we will be able to, if we push our limits, we will be able to reinvent this material. As for the research of my group, a talented set of graduate students and postdocs and even undergraduate students at Princeton, I would say that we are excited about the relatively endless design opportunities and design possibilities to understand and to engineer the mechanics of more efficient, more damage resilient materials, more functionally characterized materials compared to otherwise conventional systems. The one particular aspect that I try to incorporate in the thinking of the group is the element of surprise, the element of the counterintuitive aspect of scientific discovery that surprises us, that can hopefully surprise us every day or every time, every year. I think in science, we often pursue the known unknown. It is the gateway to the unknown that we wish to stumble upon and to access. And doing so by allowing the exploratory pathways outside the formalized research process that we have to incorporate as a research group as well.
Special thanks to Reza Moini. For the Discovery Files, I'm Nate Potker. Please subscribe wherever you get podcasts, and if you like our program, share with a friend and consider leaving a review. Discover how the U.S. National Science Foundation is advancing research at nsf.gov.